All right, let's get started again. I want to do this introduction because I've worked with Serge Koudoro for several years now on DiPy, primarily what he will be speaking about. I just wanted to sort of mention a thing about Serge. Serge really is the engine at this point behind DiPy. It's community, and he'll tell you about the project. It's a community developed project. But really, Serge is the one who's holding it together. There's sort of, maybe some of you have heard of this kind of thing, a research software engineer. It's kind of a type that we see in academia, I think doesn't get acknowledged enough. So Serge is a research software engineer, the best kind. And in this context, we're doing a workshop that's all about technical things. I think it's nice to also acknowledge that the importance of research software engineers like Serge, and just give you a sense from the perspective of research software engineers, in case, some of you might be interested in that kind of career path. But in this particular case, I'll talk about diffusion imaging and the DiPy software. Take it away.
Yeah. So thank you, Ariel, for this nice introduction. And so today I will make a quick overview of diffusion imaging pipeline using DiPy. So I don't know how many of you are familiar to diffusion. So please raise your hand if you know what is diffusion imaging or if you are used to. Oh, great. Okay. Yeah. So a big part of the audience. So that's good. That's good. So I might be able to go deeper to some concepts. I will see during the presentation. So I have many slides. I don't know until which point I will be able to reach. I will try to go fast on some concepts and don't go too deep. But if you have any question, don't hesitate to go ahead and we can talk about it. And sometime maybe I won't be able to answer and Ariel will help me. Let's see. So before I start this talk, I want to who I am. I need to present a bit myself. So I'm Serge Koudoro, research software engineer. It's been 10 plus years that I'm doing this job. I started with master in computer vision back in France. Then I moved to a private company in the Czech Republic. I work there in biometry, fingerprint detection, this kind of stuff. After that, I decided to come back in France. And when I come back to France, I work in a research lab in Paris. So I was in an image processing lab doing maintaining actually in image processing library. And I was already a research software engineer in this lab. So this was my first experience as a research software engineer. I really like it. Doing this interaction between student and professor and postdoc. And after this long experience in Paris, I moved to USA, where I became again a research software engineer in a neuroscience lab this time. And this is where I discovered neuroscience. And actually, like you, this year when I arrived to USA, I did NeuroHackademy as a student because I was very strong technically, but I knew nothing about neuroscience. So he helped me really a lot this workshop to learn about neuroscience in general. So this is a bit my career path. Otherwise, quickly what I like, you will see here. I love to travel. I travel a lot, really all the time. I love to be an expat. I love to, all the magic of being an expat. They have a ton of drawback, but you see what people don't see anymore when they are local. You are excited by stuff that, all the locals don't care about. At the same time, you got all the inside of what the tourists they've never seen. So I love this status. I'm French with Benin origin. I go there every year to Benin. I love forest because I love the hiking. I like bouldering. Bouldering is rock climbing because I'm born in Fontainebleau, where it's a big spot of rock climbing. I put the logo of basketball because I love sport in general. I love the body of the movement, the movement of the body. I'm impressed by that. I love Olympics. It's crazy. Board games. I'm a proud dad of a son who is 3 years old, and I will have the second one in 1 month if if he doesn't decide, if the baby doesn't decide to come now, so let's hope. But it should be okay normally. And otherwise, yeah, I like this game. It's real strategy time. StarCraft 2. This is the only game I play for many years. I spend with some friends. That's all. And I like, of course, coding, but I like to fix stuff more in general. I'm not the person 1 to 0 to 1, but I really like to tackle a bug, try to understand what's going on, understand, and it's in general, it's not in code, you have your dishwasher broken, I would love to try to learn the field, try to fix it instead of just buying a new one and or calling someone. So of course I fail often, but it's fine. This is my thing. So let's get back to the key learning objective of this talk. So I hope at the end of this talk, you will be able to understand the fundamental of diffusion MRI for people who are not familiar with this. Then for people who are familiar with diffusion MRI, I hope you will get a better understanding of DiPy and his CLI interfaces. I hope you will get a nice understanding of the different blocks of the diffusion imaging pipeline, and you will be able to build your own diffusion imaging pipeline with DiPy or with any other software, because at the end, all these different blocks are the same, whatever the software. So let's start from the beginning. So why do we study the white matter? So as you know, all of you, the brain relies on a big network interaction in different regions of the brain. And the best, what we try to achieve is it would be great if we could modelize this path of the brain, because all of this modelization will help to detect many disorders that we could have in general. And if I give you an example here, I give you an example of guidance of an electrode to understand to have a deep understanding of the different parts of the brain. And it's helpful to discover critical disorder like Alzheimer and etc. So a ton of them. So how do we track the connection of the human brain? So there is a several technique. So there is first the PLI technique, the polarized light imaging. So the principle is knowing that inside the fiber of the brain, you have a myelin who react to different, polarize the light and react to this polarization. So what we do in this technique, we just send a polarized light on the brain, and then following the reaction, how the light moves or deviate, we got an estimation of the fiber orientation. So unfortunately, this technique needs to be post-mortem, so ex vivo. So this is not used, but it gives a really, it is used only to really understand the different track of the brain, but you cannot use it massively. And but the big advantage of this is it gives you a very high quality data. So this is actually this kind of technique will help us to understand what we have, the different track in the brain that we have. Then you have the OCT, so the optical coherence tomography. So this is quite common and used a lot. You use it, especially it's very famous in ophthalmology for your eyes. This is used that all the time. And this is the same technique as the ultrasound. So ultrasound, you just send sound wave in your body, and then you wait for the response of your tissue. Here, instead of sending wave, you send light, and your tissue absorbs a certain amount of light, and you look at how much you lost. So this is a general idea. So this is a technique actually who works not only with eyes, but it works well on brain also. The biggest drawback, and it works also in vivo, which is convenient, but the biggest drawback is it doesn't go deep in the brain. So you have only 1 to 3 millimeters, so you don't go so far enough with that. People are working on making it more efficient to go more deeper in the brain, but currently it's not the case. So that's why it's not used really. And then the last thing that we will talk about, the diffusion magnetic resonance imaging that was developed in the 90s. And that with with an MRI scanner, we try to get the water movement of the brain, more in general. So the resolution here is in millimeter and not in like the previous technique in micrometer. So it's much larger, less good definition, but at least it gives us an idea of the full brain. So let's go a bit deeper of this technique of the MRI. So how do they end up doing that? So here was the first experiment that back in the 60s, back in the 60s, they did to discover the diffusion technique. So what they discover is when you have a molecule, you apply a small small push, I will call it a small push. So this is here your RF to this molecule. You wait in a certain strength. Here is G, your gradient strength. So let's say you push your molecule, you wait a bit, and then you push back the molecule in the opposite way, and you wait a bit, and you try to see the difference. So normally in a free environment, your molecule, after this push and the opposite push back, will come back to his initial state. But unfortunately, if it's on a constrained environment, it will not be able to go back in his initial state. So with this little experiment, we discover that this signal loss that we have between the two push is actually the movement of the molecule. So this guy, Stage start to give us the mathematical equation to describe this loss. So here's the exponential actually describes the loss of the signal, and you have the D here. Do you see my the D here, the diffusion gradient. So this is a coefficient that we try to discover, to understand, to see how much of the loss we have on this signal. And then you have other parameter here that are the delta, so the duration of this moment. You have the gradient strength, gradient direction, and etc., etc. So all these actually acquisition parameter that you have, this is what we call here, represented by the B value. We will listen a lot, the B value in the diffusion MRI. And here, S0 is our signal as a state 0. So when you do nothing, then you have your SV when you are for a specific gradient, and your exponential for your signal loss. So a few years later, I'm actually we have this paper from Basser and Co. It was in 1994, so it was almost 30 years later, who start to modelize, really start to realize that this molecule movement that we see with this experiment is actually the water that circulates in our axon in our brain. And if you apply just a simple logarithmic in this equation, you end up with a linear equation, a linear modelization. And finally, this is something that we can solve easily back then. And it will permit us to find our coefficient D of the water movement. And with this D, with an eigen decomposition, we could modelize this as a tensor. So this was a big finding in the field, and this is where everything really starts to move around. So quite recent, 30 years ago, since it's 1994, is very, very, very recent to me. So why do we need a tensor for the representation? So here it's a basic example. If we look at the diffusivity, so in our brain, we are in X, Y, Z. And if we look at the diffusivity on X or the diffusivity on Y, here I took a 2D case, but if you see it in the 3D, is the same diffusivity in Z. You see that we cannot really distinguish what is the difference between a circle and an ellipsoid. So since we couldn't define this difference, we needed another element to differentiate these two shapes. And it was easy, it just has been the diagonal. So having the diagonal information give us a bit more information about the shape of the element. And this is what describes our tensor, and this is why it has been chosen as an element to represent the different coefficients. So when we have this tensor, then we can start to get some metric from this tensor and the eigenvalue and vector decomposition. So you can get the fractional anisotropy map and the mean diffusivity. So they are all defined by those two equations, and they've been shown to be very useful to detect the neurodegeneracy or detect some tissue changes. So all of this is back in the 90s and was really a big revolution, I will call it. And this is where we start to see some software popping up to show some proposition, how to modelize and how to use it in every day. So the first software that arrived was FSL from Oxford. Yeah, I'm not wrong. Yeah, FSL from Oxford that arrived in 2000. We starting to offer tools to modelize this characteristic. Then in 2005, you have Camino as a software, same from London in UK. Then arrived Tortoise in USA from NIH, so the National Institute of Health, for people who don't know. Then you have MRTrix1 from Australia, who came to the game. And Explore DTI, who here arrive also, but by bringing a more user interface. So you can see that the DiPy is the late one. He's the last one arriving in this field, and he arrived out. And why did he arrive? So all these previous tools are very excellent. I don't have any issue with them, and they are very good tools. And I will always recommend them. But DiPy arrived out of a frustration that back then these tools were a very close source and they were monolab. So every tool was coming from one unique lab. And when you were doing research in a different environment, it was hard first to compare the different methods. When you were running DTI in one tool and DTI in another tool, you have small, tiny difference and you couldn't understand why. So try to get the source code to understand was impossible. Try to reach the lab was very complicated. So this mindset started to bother a big community, and this is why DiPy get created. So DiPy get created with very high core value to make sure that we avoid this kind of problem. So the core value was first to be free and open source. So make sure that everybody can have access, everybody in your world that you are in the middle of Africa, you can use DiPy. This is very the core value. Make sure that we have all the state-of-art algorithm, meaning that every algorithm that we put, we don't care if it's from one lab or the other. We want everything to be a big library of tools that everyone can pick and choose to build their pipeline. Of course, we want it to be a multi-lab. So DiPy started with my colleague, Eleftherios Garifalidis, who was in Cambridge back then, but now he's in Indiana University, like me. Then he was with Ariel, who was back then in Stanford and now in here. There are still many people in Stanford. There were people in Sherbrooke in Canada. There are people in Mexico, actually. It was really international lab, and this was very part of the core value to make sure that everybody contributes. And at the beginning, DiPy were focusing in diffusion MRI, but with the time, it start to have a more generic and medical imaging tool. I think about image registration, denoising, all of these kind of tools can be used in diffusion, but can be used also in fMRI or whatever other domain you work on. So I want to emphasize the importance of open source by telling a little story. So I want to make sure that Open source doesn't mean that if you put something out, that you have to maintain it. Okay, usually it's people always expect that, okay, I put something open source and you put it open source, so you have to take care of it. And this is not really open source. That open source really is, I give my product or my work to the world, and then do whatever you want to do with it. If I can help you, great. If I cannot because I have other interests, it's fine. It's there, it's for you, for the world. So make sure that you understand this concept, and no one is you. And I will give you the example of the penicillin. You know this medicine, this formula of the medicine, who was back then in the 20s. Someone start to discover the best formula of the penicillin. He was quite excited to publish it. And then back then in the 20s, he had two options. Was either he keep it on his lab, or he create a patent, block the formula for 10 years, and nothing happened. Finally, he didn't decide to do that. He said, okay, I want to help the community, and I will open source the formula that everybody can use it. Then you have some people from UK, Oxford, find the formula, and say, oh, wow, this formula is amazing. And they start to refine the form, make it more stable, make it useful, start to make some experiments in human and animals. And the penicillin start to grow up and show that it was really efficient. They decided to follow the same idea of the author, say, okay, this is amazing. Let's open source it that is available for everybody. Then the next step, the World War II appear. They move to the USA. The USA see the penicillin, say, oh, wow, this is amazing. We have a ton of resources. We want all the lab in USA to use to start to study the penicillin. We want all the private company to open source this work that we can accelerate and help our soldier in the war to feel better and to get. So all of this, and of course, all the industry start to work on the penicillin, showing all their results, and every private company start to share the result, and this grow, make a big acceleration of the penicillin, and now this is what we know today, used everywhere by everybody. So this we get thanks open source, and this is a philosophy that I think you should keep in mind, that when you have done your work and you have published it, you can just give this gift to the world, and nothing force you to maintain it after. After is another world, is another task. So here, the DiPy ecosystem. So we depend and we use different modules. So that you saw during this week, NumPy, the base for image processing. We develop our own computational neural of course. For optimization, we use a CVXPY, or we use also SciPy. The pattern for machine learning, you see scikit-learn. You had a talk about it yesterday. TensorFlow or PyTorch. This is something that we use. And this ecosystem in DiPy start to grow. We start to use more and more GPU. We have other projects that are building on us, and et cetera. So this project is built in parallel of Nightbubble. So Nightbubble and DiPy are very close. They really created at the same time. And we try to interact a lot, and some stuff move from DiPy to Nightbubble, and et cetera, et cetera. So to give you an idea of the maturity of the project, I will give you my software engineering part. I promise you it will be only this part. So it's we talk about TRL, so the technology readiness level. So this is something that is coming from the NASA. So NASA use a lot of this for their projects. So knowing that the TRL go from 1 to 9. 9, you are in the moon with a human. And 1, you are really just as the idea, oh, it would be great to. So our goal is to climb up the TRL. And I would say that in a research world, in a research actually lab, usually the TRL 1 to 4 is what I would say a PhD student or a postdoc do. So coming from the literature review, then starting to implement the algorithm, then starting to implement the software that goes, the tools that go with the algorithm, and start at the end of the PhD, first public release, putting out, and hoping for the best, that it is used. Then when I arrived in DiPy, they push it more, and they push it more in TRL. They were already in a TRL 4, 5, almost 6, where they make sure that all the best practice of software engineering was implemented. So by doing a stronger software engineering system, using some design pattern to make sure that everything is reusable, easy to maintain. And then they add heavy testing, make sure that every single function in DiPy is tested, every single function is documented. And you can see that we have a huge documentation in DiPy. And of course, starting since it was a multi-lab, start to use the community that we started. It was very great. So all of these elements make a DiPy a great and sustainable software to help a researcher. So when I arrived in DiPy, they were already in 4 and 5. It was great. And then when we see at the other level of TRL, 6, 7, 8, 9, then it's really hard to reach 9. 9 is packaged like scikit-learn, actually, who are already massively used in all companies and everywhere. I believe that we are in TRL 6, at the end of TRL 6, where our tool is used by multiple research groups and validated cited a lot and validated by everyone. And we start to see some application in different clinic of this package, some use of this package in clinic, in startup. Many startups use DiPy, and some hospital use DiPy. So our goal is now to reach a strong TRL 7 by simplifying. So here's the TRL 7. How we can reach that is by reducing the manual effort for everyone to use this package and make it accessible to everyone via CLI that I will talk now about. And user interface, we don't want to do that really, but we might have to do it. So we started to work on it and make sure that we can,
One question on the TRL and readiness and aspect. Since you were saying it's going to start to be used in clinic, do you have any, I mean, are people doing some kind of a certification aspect for FDA, or is that legal and aspect is being worked on, or what's your...
So can you repeat the question? Just I'm gonna ask.
So the question is about the different legal aspect if we have some clinical use data to certify our tools. So we see, for example, I would give you the example of Sherbrooke, who is a big contributor of DiPy and start to create a company who succeed to make FDA approve a whole pipeline, but under the hood, they had to accelerate some of the DiPy tool. So they have their own implementation to make it even faster. And they also make sure that they couldn't FDA approve only one method. It should be a pipeline for a specific study. So in this case, I know it's an ambiguous response, but it's yes and no. You see what I mean? Yeah. Okay. So now that we got a big overview, let's move on to how to build your diffusion imaging pipeline. So first, DICOM. So I suppose after you get your images, your scan from your scanner, it's very standard to have them in DICOM. I can only recommend this tool, DCM2Nix, that permits you to convert your DICOM to Nifty file. So Nifty file is a standard in the domain. I don't know any software using directly DICOM. Most of the software use Nifty. So I think it's a mandatory step actually to transform your DICOM to Nifty file. So this is here the command line to convert your folder. So I don't know if here anyone have the compound. This is really an easy way to do it. And then the important part is the installation of DiPy. So you need to have a valid Python environment, of course. And then to install it, you can do a pip install DiPy. The -u is update to have really the latest version in case you already have a version installed in your laptop. Or you can use the Conda environment. I don't know if you talk about Conda, but it is the same principle, Conda -c, Conda Forge, DiPy. If you are courageous or adventurous, I would say, you can also install the official developer. This is very unstable. It is updated every 2 or 3 times per week. For sure, you have all the latest. You have all the latest algorithm. That's quite exciting, but you could also have the latest bug. So that have not been checked or have not been. So I wouldn't recommend, if you are not comfortable with developing, I wouldn't recommend to install this one, the developer version. But if you want to have really the latest and you know what you are doing, feel free to install it. And it's updated every 2 days, so it's really convenient. So now that we have the pre-requirements, let's go to the diffusion imaging pipeline. So this is quite common as a diffusion as a pipeline. So first you have your preprocessing step to clean your data. Then you go to the fiber modeling. So we go to one space, which is here your image with a different representation of your image. I will explain it more later. Here with the ODF. When you have the ODF, so your data represented in a different way, you can start to do the fiber tracking. So here with this end, you start to get all your parts of your brain. And when you have all the parts of your brain, you can start to make some post-processing analysis. So start to cluster the different parts of your brain, start to get some analytics, etc., etc. So the pipeline here is quite straightforward. It's very standard. And this is what everybody in the field actually does. This is But now that we know what everybody does, let's go more deeper in each step and try to understand how you can adjust each step following your data. So of course, I put some, I forgot to say that, I put some box in color to show you what we have in DiPy. And to currently in DiPy, we have more than 50 command line, which split in these different steps. So in blue, the pre-processing one that we will talk about later. Then the reconstruction part, where you do all the fitting methods. And tractography part, here you have only 2, but contain multiple methods. Then you go to the tractometry. So the tractometry is the analytics, I will call it, of the post-processing of the fiber. And then you have some utilities function that are needed to make your life simpler. So like I said before, we will try to add more and more command line to make it easy for user to use DiPy. Otherwise, everything, of course, everything is accessible if you program in Python. So why do we do pre-processing? So pre-processing actually is I find it strange, but the idea is just to clean up the data, to have the data the most normalized as possible, to make sure that we can compare between a subject. So that's the only goal of pre-processing. Make sure that everything is quite standardized. And when we have the standard, then we can go further. And unfortunately, the MRI scanner bring a ton of artifacts during his acquisition. It's not a perfect technology, plus the different environment interact, and that's why our data can be quite disturbed. So a pre-processing pipeline will be something like that in the diffusion imaging. So this, again, this is a standard. But in all this pipeline of preprocessing, you have many steps that are optional, some that are mandatory, etc., etc. For example, here, you will start with your DMI data, which is a nifty file, and then we go to reslicing. Reslicing is called also resample, and I will talk about it after. So this step here is optional, for example, reslicing. Then denoising. Denoising, most of the time with MRI scanners, you cannot escape noise. So for sure, this is a mandatory step that everyone will have to do. Then you have Gibbs unringing here. This depends on the scanner, same. So this is a step that can be optional. I will explain more what it is. Motion correction, this mandatory. No one stay very stable in a scanner. So you always have motion. So this is a mandatory one. Bias field correction depends on your data. I will say most of the time is mandatory, but it happens that sometimes you don't really need it. If you have very, very, very high resolution data, and it's okay. Then you have brain extraction, mandatory, or every algorithm needs to have only the brain and not the skull. I would say, yeah, almost all. So this is mandatory. And then you can have some registration to T1 template, another modality to make sure this is very optional. So let's start with the reslicing. So the reslicing or resample is the idea of some scanner acquires the data in an anisotropic way, meaning that one voxel doesn't have the same size in each dimension. So instead of having a voxel size, for example, of 2 to 2, that we know that they are exactly the same, you can have sometime a 2 to 7. That slide, the voxel is really elongated. So you have to know that when these anisotropic data appear, honestly, no software in the diffusion imaging, just for MR2X or DiPy, work well with anisotropic data. We always assume that your data is isotropic. So of course, you will be able to run your algorithm. They will give you strange results. You won't understand why. And most of the time is because your voxel is not isotropic. So this is something that you have to make sure when you start to check that. For us, we have a command line named DiPy info that gives you information about your nifty file. You look at this. With this information, you know if your data is isotropic or not isotropic. And if it is anisotropic, you use DiPy reslice my file and the voxel size that you want, and it's reshaped as you want. So imagine that you have an image very anisotropic, like a 2 to 7. Usually, we recommend that you don't try to reslice to 2 to 2, but you try to find the middle ground between the two dimensions. So you will do a 4 4 4, that the 7 go to 7, and we try to reach a middle point. So this is what is recommended generally when you need to do the resize. So here you have a quick example of a DiPy info. DiPy info in the terminal gives you that. Here you can see some information like the data size, X, Y, Z for your volume. 160 is the number of gradient. So here we have 160 gradient. And the coordinate system here, we are in RAS. And the voxel size here is a 2 to 2. With another type of data, you can see that here the voxel size is 187, 187.2, and we give you the information. Please reslice your data to make sure that is isotropic before you continue. Then we tackle the denoising. So the denoising is a big part. People still study denoising. And denoising actually is split in different categories. You have first I don't know if it's not big. So we have a command line named DiPy denoise enemy. So use NeuroHackademy technique. So those technique is part of the family that we call the self-similarity family. So you have the block matching. So BM3D algorithm that we didn't implement, but it's the same family. So the global idea is in one area, okay, you take all the different patch of the same area and you believe that they are the same similarity. And because they have the same similarity, you can deduce the middle patch and correct it. So, or average it. So this is really the global idea. I'm really simplify as maximum. If you want to go more in detail you have the different paper here to understand more in detail those algorithms. And then you have the second family that I will call the low rank approximation. So DiPy denoise LPCA and DiPy denoise MPPCA. So the low rank estimation is the idea behind this family of algorithm is from a matrix that you have, you can deduce another matrix. You can have a simplified matrix of it with the most relevant information. So for that, you use, for example, SVD, single value decomposition that come from one matrix, your data, so your block with voxel, and then decompose it to 3 other matrices, and you keep only the matrix with the most relevant information. So this is again, this is oversimplified, but it's really to give you the general idea of those family of algorithms. And actually today, MPPCA is the most used algorithm in the field. It gives a really excellent result, and people use it a lot, MPPCA. So I will recommend, of course, a lot to use. You cannot go wrong if you go with MPPCA. Then you have our algorithm that we developed a few years ago, 2-3 years ago, patch to self, which here now make a guess about noise. So we say that the noise is statistically independent between different volume. So meaning that in each volume, the information kind of stays the same, but the noise that you take in different gradient will be very different. So for that, what we do, we use a machine learning I put quote, or self-learning method, where for each gradient, for each volume, we extract one volume. Okay, this become our label, our reference. We do with the other view regression. Okay, so we take every voxel of the different volume, and we do a regression, taking that the volume that we extract is our references, and we do that over each volume. And this naturally we start to detect what is a noise and to remove it. So the patch to self is quite new, but show amazing results, and actually even better than MPPCA. So we are very proud of this technique. But at the same time, we saw that patch to self, like every algorithm, has some drawback. And we realized that when you have very few volume, few gradients, it can sometimes perform a bit less. And that's good. So MPPCA would be better. And we saw also that on some scanner, strangely, we always have this feedback, Siemens scanner, MPPCA works always better than patch to self. So I don't know what is so specific with the noise of a Siemens scanner, but we need to study that. So I can only recommend in general a patch to self, and if it doesn't give good results, then you can switch to MPPCA. Actually, we have some collaboration where they do the cardiac MRI. This is a new trendy. So they apply diffusion MRI on the heart, and they try patch to self, and sometimes it works, sometimes MPPCA works different, much better. So I recommend to use it. And then we have the sparsity. I want to talk about this category of denoising. We don't have any algorithm implemented in diffusion MRI. It doesn't show the best result, so that's why we don't spend especially time on it. But you can always, if your research is about denoising, this is always something that you can explore. A small note that in this four category, the sparsity, self-similarity, and the low rank, their main assumption is about the signal. It's guessing how the signal could be. And this is a huge difference with the patch to self, where we try to guess how the noise could be. So this is really two different points of view. And this is what makes a patch to self quite unique, because we make assumption on the noise and not on the signal. So Gibson ringing. So Gibson ringing, here you can see the rings here. I don't know if you see with the screen, and it's not so much visible. Sorry about that. But you need to know that the image of a scanner, the MRI scan, are reconstructed using a FFT, so Fourier transform. And when he does the decomposition using the Fourier transform, of course, to do this compilation, you could use an infinite number of sinusoid, but unfortunately, we can't have an infinite number. We have a certain number of a certain amount of sinusoid, and sometimes the wrong one can be there. And this is where the Gibson ringing is useful to detect those signals that we don't want and start to extract them. So to give you really a rough idea is you are in the radio. Okay, when you listen to the radio, you have the signal which is perfect. You start to switch to another channel, another frequency. You start to have some noise. And this noise that sometimes you listen on the radio, this is maybe a frequency that you don't want. And still appear, you still listen this and you say, why are this? And you try to switch your. And here, this is the same principle. So now we try to tune to say, hey, how can we remove this frequency that we don't want? So using FFT is very efficient for that. Then on the pipeline, you have motion correction. Motion correction is to detect the movement of the brain. So the movement can be two types. Either the movement, the intravolume. So here is very common here. The intravolume is very common in the toddler brain. Okay, so they move a lot. So you can see the sites moving. Or with more adults, you have between a different gradient, you have some. So it's necessary. You need to use, for that, we use an affine registration. So I could go in detail how we could, how you do a registration, but it's not a topic. If you have any question on how image registration work, I can explain it later. In the same topic, I put it here, but it could have been somewhere else. There is a eddy current correction. So actually, currently in DiPy, we don't have any algorithm for eddy current correction. Most people use FSL, which is great. But to get the idea of the eddy current correction, it's just a phenomena from the different from the scanner. So when you switch a gradient, you have a kind of a Faraday effect. And this is something that can be easily corrected by doing a rigid registration and an intensity normalization, intensity correction. So why we don't do it? We don't do it in our lab, or we do it sometimes, depend. It's just because the patch-to cell that we see before as a denoising algorithm does an intensity reduction, does already an intensity normalization. So it corrects the intensity in different places. And if you combine that with a rigid registration, which what FSL does, you have kind of the eddy current correction. So you have correcting the displacement and correcting the intensity. So combining these two methods does the eddy current correction. Of course, we could do better and have a specific dedicated algorithm if the intensity are really crazy, because the intensity normalization is really the hardest part, but it's not always necessary, depending on your data. Brain extraction. So here, we try to remove the skull of the brain. There is many methods for that. In DiPy, I will highlight only two methods that we have. There's a median SU, that this works well on the DWI. So this method uses a median filter to smooth your data. And then you use the Otsu method. The Otsu method, what it is just, you have your picture, you take an histogram of your picture, so you have all the different intensity, okay? And then you try to maximize the variance between. So you try to find the best threshold between your histogram to split your data. So if you have an histogram doing like this, super high here and super low here, it will split here and we say, okay, this is a skull and this is your data. It works very well for DWI. It doesn't work at all for T1 image. I suppose in the fMRI stem, it doesn't work at all. And because of that, we have to implement another method, EVAC Plus, which is a deep learning method. This I won't go in detail. One of the many deep learning methods. There's also a method for brain extraction, and you have SynSeg, another deep method, and you have BET that is very famous and one of the first one. Who here we take a structuring element, and we try to increase it and detect the brain like this. So as you understand, preprocessing, cleaning your data is a huge topic. It's really very, very huge. And I won't spend more time on it. I will recommend you to read this excellent paper from so what next in diffusion MRI preprocessing, who lists you all the different preprocessing that you can do and give you some advice. You can see that here in this schema that you have a very all these steps that you can do, and every step has sub-step. So this is really a huge topic to clean your data. Every lab do differently because it depends a lot on your data. There is not one answer. And there is a standard, but the standard is highly customizable. And yeah, so I will recommend you to read this paper with some recommendation. This is a nice literature review. And if you want to know more about preprocessing your data. So of course, we have two other, we have other command line that I show here, DiPy align affine and SYN for nonlinear registration, and correct bias field, same. We have multiple methods, either for DWY or either for T1, which are very different. Okay, so we tackle this huge topic of preprocessing. Let's go to reconstruction. So reconstruction now, the goal is to start to modelize the fiber of the brain. And we want to know what is the water movement of the brain and understand the physics actually of the MRI scanner. So most of the time he's here. When the scanner works, he has a specific space to work. Then with FFT, he goes to the image space. And then when we're in the image space, we know that the scanner uses the Fourier transform. And then we try to go to another to have a new representation of the image and go to the ODF space. ODF meaning the orientation distribution function. I will tell more about this in a second. So in DiPy, we have huge amount of reconstruction method. We have more than 30 methods for reconstruction. It's a lot. It's a lot. We really implement what everybody does. So it can be a headache to choose which one, but we can explain you. I will try to explain you how you can pick one. So let's enter to a bit of theory. So for the reconstruction methods are split in two big categories, which are the phenomenological model, sorry for that, and the mechanistic model. So the first model, the first category is represent all observable property without any guess or any assumption. So we look at the signal row and we don't do any assumption about that. And the mechanistic model start to guess, introduce some guess. And this is where you start to do some microstructure, you start to introduce a microstructure. So today, I will not talk about the mechanistic model. This is still, I still call it new, even if the field is currently very active on this model, and I will focus more on the phenomenological models. So these phenomenological models are split in two categories, two subcategories. So first, you have the Gaussian diffusion modeling, where you have the DTI that I explained just before, and the DKI, another method. So the difference between both, you can see on the equation, is on the DKI, we introduce a new element of the original element, which is the kurtosis. So the kurtosis just explain the so let me put this element. So the DTI have, like I explained to you before, have only 6 parameters, and the DKI have 15. So every voxel on your image is represented like a Gaussian, okay? We do this assumption of it is a Gaussian because we do this assumption that the water is free to move everywhere. When DKI was introduced, it would say, hey, no, the water is not free everywhere. There is some part in the fiber that it is constrained. So because of that, the Gaussian model that you have on every voxel is not perfect every time. So sometimes you have more, sometimes you have less. And this is what we call the kurtosis, showing that this water movement is not always perfect, and the residues that we call the residues of movement that we call the kurtosis can be different. And this introduces 8 more parameters, and this theory permits us to permit the community to start to not only have one fiber in every voxel, but start to have 1 or 2 fibers, represent 2 fibers in different voxels. So this is the first family. And then you have the other family, which is orientation distribution modeling. So the big difference between these two families is in one family, in one voxel, you represent it as a Gaussian model. Now, in one voxel, every voxel is kind of this ODF, or orientation distribution of your water. So here, you have 2 famous algorithms, CSS, CSD, where you have the same description. So when you look at the equation here, the signal is equal to the response function, the sum here of the response function, plus here of spherical function that we have here. Our spherical function actually is the same as our ODF function that we have here. That is more detailed. So here we have E. It's called E, but it could be a S. It has been chosen E because it is a normalized, the normalized signal. But you could see it as a, where is my cursor? So yeah, so see it as a SQ with here this element that this is our spherical function. So the spherical function here is a great representation on the difference between an ODF and so what people call DODF and what people call FODF. So the DODF that you have in CSA here is your classical spherical function. And when you convolve here a response function, so what is this response function? It's just that we look at the fractional anisotropy, so the FA, and we look at what is very anisotropic, where we are sure that we have only one direction. We are certain. So we take only 1,000 of voxel, and we know that, okay, the water go to this direction, and we are sure. So now that we know that this is going to this direction, we modelize it. We know that it's going to be one fiber in one spherical function in a specific direction, okay? And then we convolve this with the most general case, and we got some thin FODF, more descriptive element that you have here, okay? So this kind of finding was quite a revolution and helped a lot for later. So I talk about the spherical function and the spherical harmonic, but when you are not familiar with the field, when I was a student, you always say, but what is a spherical harmonic? And so let's demystify what is a spherical harmonic. So a spherical harmonic is just simply a spherical function. It's just a Fourier transform that you apply where you apply the signal on a different domain. So here, this is a sphere. Okay. So when you look at this representation, if you here you have a classical signal over time, this is a standard where you can apply the Fourier transform. And instead of applying the Fourier transform here on a classic signal, now you apply it on the sphere, where the signal is around the sphere. Okay, so the signal around the sphere represents all your gradient. So, of course, when you say that, most of the part of the people will understand, say, okay, yeah, it's obvious. Now I understand what is a spherical harmonic. But many people will say, okay, I understand what is the logic of the spherical harmonic, but what is a FFT actually? Because I'm not familiar with math, and I can understand this problem. So let's go deeper. And what is a FFT? So what is a Fourier transform? The Fourier transform is just a decomposition of a signal. And when we decompose the signal, we change from one domain, is a way to describe the domain in a specific moment, to a different domain, which is a frequency domain. So if we take this example here, where you have your signal on the top, you apply the FFT. So here's your signal, you can see it as an orchestra, you listen to your music, and you want to decompose it. And here you say, okay, I applied the FFT on my orchestra. And after that, I know that, okay, I have a bit of the trumpet, a bit of the guitar, a bit this quantity, and I can easily. So by applying the FFT to the signal, we went from the domain when we have the signal and the time to a frequency domain when we can describe more our signal on how it is. So the FFT principle is very simple to understand like this. Of course, the FFT can be applied to everything. Imagine that our domain is an image, okay? So now our domain is, to describe our domain with an image, this is a pixel intensity, the value of every pixel, and the pixel position. So when you apply the FFT to that, you will have some texture, some different elements that help you to detect actually different elements in the image. So this is how it is used in image processing, the FFT. But in a diffusion world, we use it the same. So here, if you look at the equation of the FFT, you see that here you have the frequency domain of our signal is a sum of all our different exponential here, of different sinus here. Okay. And yeah. And you can see that this equation is very, very similar to the diffusion equation that you saw before. So when you apply the FFT in diffusion imaging, it is exactly the same. So here you have your signal. We are in a Q space, okay? So this we call the Q space diffusion area. The signal width. So here, imagine that this is a signal of one single voxel, of course. So you apply it to all your voxel. You have your signal for every gradient of your voxel, so every gradient strength, okay? You apply this FFT on this domain, diffusion domain, and you have the new representation which represents your ODF that you have here, and this ODF that we call spherical function can be described in multiple spherical harmonic. So it's a bit of this sphere and a bit of this sphere with this shape, a bit of this sphere and the other shape, etc., etc., etc. So these different elements of the spherical function are called how you define the spherical harmonic depend on different bases. So there is multiple paper how you define the spherical harmonic. I won't go more in detail into that, but we have two major bases in diffusion MRI. So you have the Decotre basis and you have the Tournier. This is what they use in matrix. In DiPy, we have both. You can switch in both. Depending on what you want. So this is how you describe your signal. So now that you know what is the FFT, and so the FFT is just changing domain. So we go from one specific domain to the frequency domain to describe our signal differently. We can look at what is the Q space. And the Q space actually is just how you acquire your image with your MRI scanner. So if you look at the history of the Q space sampling, you can see that the initial history here with the plus gradient spin echo that I explained you before. Then we start to add more the diffusion weighted imaging. Then we go to the diffusion spectrum, more data points to describe. So every point is a gradient strength that we apply to see more how we are shaping the water. Then we enter to the diffusion tensor imaging, who was a revolution, where we have 6 points and we start to be able to modelize as a tensor. And then you start to get crazy with the diffusion spectrum imaging, which is more a Cartesian model. Then the single shell imaging, then the multi-shell propagator imaging, 2008 and now the super multi-shell hybrid diffusion imaging. So it getting crazier and crazier. And it gives us more and more information, data are bigger and bigger. So today, if you have data, most of the time, it will be a single shell or multi-shell acquisition. This is what is very common now. And don't forget that he just described how you acquire your image. So like I said before, in DiPy, we have more than 30 algorithms to apply the reconstruction. And you have a nice documentation where we tell you for each algorithm, we have a tutorial. We tell you if it works with single shell data, with multi-shell data, or with Cartesian data. You can see that some work only for multi-shells or none. We give you also how initially, what was the first parameter of this algorithm. So to see if it's aligned with what you are trying to do, for you are going outside the border, and it gives you the paper reference you want to know more about it. Of course, you see in orange here, every method have a tutorial when we explain to you how to use this algorithm and what is the best case to use and what's the bad case to use. So feel free to go to check on it. And yeah, so now that we did the fiber modeling, let's go. Now that we change space, so we again for the image space to our diffusion space, let's go to the fiber tracking of the pipeline. So the fiber tracking is simple. It's just going from now our diffusion space. We try to start to draw line to represent our track of the brain. So you can see that when you do that, when you do that, you can start to have a million of streamlines representing all the parts of your brain. And to do so, you need a different step. So first, you need an image in a diffusion space, of course. You need your direction strategy, how you select the direction, actually. And actually, the difference between every algorithm will lay on this step, the direction selection strategy. So every time you have a different method, is mainly just how we select the direction right now. So you need the tracking mask. So usually it is the white matter. So you don't want to track your data outside the tracking mask. So this is something that you already have most of the time. You take you threshold your FN, your tracking mask. You want your seeding mask. What is the seeding? The seeding is where the point where the tractography will start to track every single step of your diffusion imaging. So usually we do one seed in every voxel, okay? And every voxel, the tracking algorithm will look at that and will say, okay, I will start with this point and I will see until where I can go. When I reach the gray matter, I stop, or if I reach whatever condition, I will stop, okay? And then, of course, you have different options to see the step size, how much you need to advance in your tractography. If you do big step or just tiny step, the curvature, how can I turn? If I can do a 360 degrees or just a little angle, it helps a lot, and etc., etc. So the big challenge of the tractography is when you encounter, of course, a different intersection. So here in the classical, so there is a nice paper talking about that, saying how we can improve tractography to avoid a false track. And it's not obvious, because when you have a discrete here, okay, so you have multiple. What do? Do you pass just straight away? Do you pass like this in diagonal? Do you just go down and go up and then? So this is the biggest challenge right now of tractography, is how you describe this kind of area. So here you can see up is straight away. Even with your eyes, you can do tractography. It's very obvious. and it's a nice area. But some areas are not like this at all. They are combined with multiple direction, and so the whole field is working on how we can guess, how we can get enough information to take the right decision on where to go. So here is a nice presentation. Is it here a ton of crossing? What do we do? So this is many people is working on this to improve the tractography, and yeah. So we have a command line, of course, to do that, named DiPy track. DiPy track, you give your file. Your file here is a PAM file, but it can be a Nifty, but is a data that is in diffusion space. It can be a tensor, it can be whatever ODF file that you have. Then you give, of course, your stopping criteria, seed density, how much starting point you want to put. Some people they put 100 points in one voxel to make sure that we start in the right place. Some people they just decided to seed only on the surface, okay, and see from this surface where can I go. These are depend of what you are trying to do, and yeah. The tracking method. So I told you here we have deterministic, but you can have probabilistic. You have a party. Yeah, you have many methods, and I told you, like I told you before, is the method is mainly how you choose the direction. So usually you need to read the article to get an idea of how do they select their direction. That's all. And we have a DiPy track, a PFT, which as in the future, this command line will disappear, but we still have it because the PFT method is great. So the idea between PFT is when I track, okay, I reach the gray matter, and before every algorithm stop, this one backtrack a bit and try again to continue. And then stop, backtrack, continue, and backtrack multiple times to see until which point you can get. So this is a nice technique, and it can be actually combined with all the other techniques where you choose a direction, but this one backtrack. So that's why this one will disappear, since it can be combined with all the other methods. Now it's just used with only one method, which is problematic. So here you have some tractography result, depending on different methods. Okay, so you can see that how you select your direction can give you quite a different tractography result. And for now, here this is the best method, and the method is named PTT right now. Okay, so how to visualize your tractography? We have a command line for that named DiPy Horizon. It allows you to see all the different tracks. I can make you a demo. I will make you a demo if I have time, quickly. It allows you also to visualize a classical T1 or DWI image. Yeah. So now that we did the fiber tracking, it's time to tackle the post-processing part. And why do we need post-processing? So now that we are our full brain full of track, what we are trying to do is, of course, to detect a different part of the brain, because all the disorder usually target one specific part of the brain, and we want to be able to detect every part of this brain and get some analytics of this different part of the brain. So to do that, what we do, we have a different command line named DiPy SLR, DiPy recombundle, DiPy refine, that permit to do that. So the principle is we have a model, an atlas, where we have the perfect brain and the perfect bundle. So now that we have the perfect brain and perfect bundle that have been validated by the doctor, our new image here that we just generated, we try to align these two brain, these two tracks. So we use the DiPy SLR to make sure that we are in the same space as a model. When we are in aligned and in the same space on a register, okay, this is where we can start to use recombundle. So what recombundle do? We use the model. We have all the track. okay? And it just takes the first track, start to search using a classical distance function. See, try to get, okay, which bundle in this brain is enough close to each of these track. When you get all this track, you get out a specific track. And then we have a function to refine, because some tracks doesn't mean anything, and the shape doesn't make sense. So we clean our bundle to have the correct shape. So this is a really in the principle is it's really simple, hard to create, but the idea is very simple. So when we have every single bundle and our global, this is where we start to do tractography. So now we have the FA and different metrics that we compute in our diffusion image. We have our bundles. We apply those metrics in our bundles. And by applying those metrics on bundle for different subjects, we can start to see some, we can start to get some analytics and discover different disorder. So this framework that we have is named Buran. So we have a command line named DiPy Buran, but also there is what IL team is doing, IFQ, that does also an amazing job. So you have two frameworks, and actually I believe that only the DiPy team right now is working on tractometry. I don't know any other tool. Do you know other tool doing tractometry?
Yeah, there are.
Yeah, I don't.
Like TrackSeg has ways of.
TrackSeg just segment, but doesn't do the analysis after.
It will give you also.
Okay. Okay. So you have other tool coming. This is really a new field. This is an exciting field, and people are working more and more on this.
Oh, and I should make Tracula. Tracula?
Yeah, Tracula. Yeah, that's true. Yeah, there is Tracula. Yeah. So yeah, so many tools are coming up to do this thing. So so of course we have some utility function on our command line. I won't go on it, but DiPy fetch to get your data, DiPy math if you want to facilitate the work, extract your B0, extract your some shell, convert your data in a specific way. So all these utility functions are very classic and make you win time. So if you want more information, of course, we have our amazing documentation. So you go to docs, CLI, you have a different tutorial on how it works. You have also the CLI API to explain you every parameter of the function. And you can always do a DiPy tab to get the list of all the function, or DiPy help, DiPy your command help to give you all the information. So this is very classic to every command line interface. So I won't go too much in detail. So what next? What next for DiPy? So for DiPy is really to continue to grow and continue to try to achieve the tier 7 and 8. So to do so, we need to increase the number of DiPy workflows, making tools much more available for every user. We need to introduce a basic user interface. Maybe next year we'll have a basic one. I believe so. Next year we'll start to have one, and feedback will be very welcome. And but the biggest important point is increase validation against clinic gold standard. This is a major point that we want to achieve, and this is only through collaboration and making sure that we understand, we obtain what is found on the literature. So I can only call you to be part of the community by providing feedback if you use DiPy, by sharing data. If you cannot, I know it's tricky now in this period. You can build collaboration and make it private for a certain amount of time, but it's enough time for us to understand what is going on before we give to the world a better software. So a quick word that we have a DiPy workshop every year. Yeah, every year, like NeuroHackademy in March. Next year will be March 16 to 20. It's coming soon. I don't know yet the speaker. I don't know yet but it's coming, scheduled. If you are interested, feel free to register to get an idea. Yeah. So that's all. If you have any question, feel free to ask. I will be happy to answer. I think I'm on time. I was a bit fast, but I hope you got a global idea and you got the key learning of this presentation. Thank you very much. Yeah.
Thank you for your talk. It's about how to deal with harmonization when you have a data set that is multi-site, and what are your recommendations for using DiPy?
To do data.
The harmonization. If you have different scanner types.
Yeah. This is a complex topic too.
So maybe repeat the question.
So the question was about data harmonization, some recommendation how to do the data harmonization when you have data from multiple sites and multiple subjects. I mean, actually, we are currently working on a project to improve that, the data harmonization. So I can't tell you really what is the best advice on this. Actually, the name we work with the Vanderbilt team, and the project is named. I have a memory loss right now. What was the name?
You can post it later also.
Yeah, I will post the URL there, where we explain how we do data harmonization and how we can. But no, it's a complex topic also because between different sites, usually you have different scanner. So because you have different scanner, you have different preprocessing, because the scanner doesn't give you always the same result, and you have sometimes slightly different configuration. And yeah, preprocessing is really yeah. Is there any other question? Yeah. About
the fiber tracking.
Okay, yeah, fiber tracking.
You have the direction, right? And there's like a magnitude, I guess. So what does the magnitude like correspond to?
So when you have your, don't forget that for every voxel, you have your ODF, okay? And the ODF represents your water movement, your water diffusion. So every amplitude in your ODF gives you the probability of your water to go in a specific direction. So if you have a less kind of, here is represented in red and blue. For example, if you have a blue point, if you see the center is always blue because the water have higher chance to stay in place. And when you have higher amplitude, the water have more a higher probability to go there. So for the tractography, actually we take that into account. So you have some algorithm, they will just take the highest peak because this is the highest chance that the water will go to this direction. Some algorithm will say, okay, now we won't take the highest peak, it's not relevant. In the probabilistic, we will take these small windows, all this peak, and we will look at the next one, and we'll take a probability estimate, a chance that you will much more go to this direction than this direction, and not just take the highest peak. So this is what I mean. I don't know if he answered your question. Yeah.
I mean, it's more like a probability of which direction there's multiple, but
Yeah. So yeah. I saw there was another question here. Yeah.
How big the fibers have to be for this to be reliable?
So how big has to be the fiber? So we say that the scanner in any case can take only in millimeters, right?
So you get a millimeter.
Yeah, in millimeters.
Yeah, a millimeter band.
Yeah, maybe you have a. I don't know exactly how much minimum, but I know that scanner. I mean, depend on the scanner, really. Do you have an answer for that?
It's a fairly tricky question to answer. I think it depends a little bit on the measurement that's being done. One of the challenges here in answering that kind of question is that you can measure at many different spatial resolutions, but also there's other parameters like the the diffusion weighting set that you use,
Mhm.
that will also have an impact on your ability.
Mhm.
Generally, that part of what's kind of magical about diffusion MRI is that it probes motion of water at very small scale.
Yeah.
So the motion of water molecules here that this method is sensitive to is microns, but it's over, large boxes of millimeters. So you're kind of averaging, you're getting a powder average of this. So you can measure very, very small axons, but only when there's a lot of them together.
Mhm.
So that's
Mhm.
maybe that answers, but we can
Yeah.
we can discuss that more.
Yeah. Okay. No other question? Thank you, everyone. And if you have any question, again, feel free to, all my life now. So feel free to come to chat and